Okay, so good morning. We will continue our discussion on the slip boundary condition for gas flows in microchannels. So, originally it was Maxwell who proposed an idea to account for the microscopic cause of slip into the macroscopic continuum models. So, one of the easiest ideas is you can draw an analogy from our reflection or scattering of phonons or electrons from the boundary, either it could be a specular or a diffuse kind of scattering. And we have already solved in the nanoscale transport, we solved the Boltzmann transport equation applying the boundary conditions, and the first consideration was the diffuse scattering, right. So, in that what we assumed is whatever energy carrier that is coming out of that boundary is having the value of equilibrium. So, that is based on, for example, if you talk about the Bose-Einstein, the non-equilibrium function of the phonon or electron which is coming out in the plus F plus coming from the bottom wall will be equal to F equilibrium corresponding to that temperature and frequency. Okay. So, temperature whatever the boundary is maintained at. So, now similarly you can imagine these gas molecules at the micro scale also do the same go through the same kind of phenomena. So, they encounter the boundary, and a part of this a fraction of this you can say gas molecules can be kind of absorbed or thermalized by the boundary. Absorbed or thermalized means they come out, they are emitted with the distribution function equal to the Maxwell-Boltzmann distribution function. Okay. So, that is the fraction sigma, and the other fraction 1 minus sigma are simply reflected. Okay. So, are perfectly reflected in the sense they are like a specular reflection, like a mirror image reflection. Okay. And we know already from our knowledge of nanoscale transport that whatever is emitted diffusely, scattered diffusely, so that is not going to conserve momentum. The momentum is actually destroyed in the process, and because whatever incoming gas molecule and whatever is coming out of the boundary have different values of the distribution function and therefore different momentum. Okay. So, therefore, the emitted gas molecule will be thermalized based on the temperature of the boundary. So, based on the Maxwell-Boltzmann distribution function, you have to calculate what is the value of momentum for this particular emitted gas molecule. Whereas, in the specular scattering, it is momentum is perfectly conserved. So, only the direction is changed. So, the outgoing will be equal to the incoming, the same momentum it possesses, and therefore, in that case it does not really understand what is the condition of the boundary. Okay. The gas molecule which is coming out of the boundary does not really have a feeling of what is the condition prevailing on the boundary. So, therefore, these are two distinct on the different ends of the spectrum, two different extreme cases. So, one in which it completely forgets its so this is like it loses its memory. So, it's emitted equally in all the directions based on the condition at the boundary. So, that is the diffuse scattering phenomena. See, the other is completely ignorant of what is the boundary phenomena, boundary condition. So, it is only emitted with the momentum of the incoming gas molecule falling on the boundary. So, therefore, Maxwell proposed that you can assume of the total number of molecules, fraction sigma will be emitted like the way diffuse scattering takes place, and the rest 1 minus sigma will be emitted the way specular scattering takes place. Okay. So, therefore, this sigma he called this with a name called the momentum accommodation coefficient. Okay. So, that means it tells you whether you conserve momentum or not. Okay. So, the expression for this you can say that I mean you can either write components in the tangential or in the normal direction, but the general philosophy is you define the momentum accommodation coefficient as the ratio of the difference between the incoming momentum minus whatever is coming out of the boundary, the momentum of the reflected or the energy carrier or gas molecule which is leaving the boundary, divided by the difference between the incoming momentum and the momentum according to the Maxwell-Boltzmann distribution function. Okay. So, that is your Pw, okay. That is your thermalized value based on the Maxwell-Boltzmann distribution. So, what does it mean in the case of diffuse scattering? What should be this value? What should be the value of the momentum accommodation coefficient? What do you think will be the value of PR? PR will be equal to Pw in the case of diffuse scattering, because everything is absorbed, thermalized and emitted from based on the conditions on the boundary. Okay. So, it is emitted like your condition, we put F plus is equal to F equilibrium, that is your diffuse boundary condition. So, therefore, in the case of diffuse scattering, your sigma will be equal to what? 1. Okay. So, whereas if you talk about specular scattering, what happens to sigma? 0, because PR will be equal to Pi. Okay. The momentum is perfectly conserved and it does not have any idea about what is the momentum depending on the Maxwell-Boltzmann statistics. Okay. So, in that case your sigma will be equal to 0, it is a perfectly reflecting surface, and the other diffuse scattering will be sigma equal to 1, right. So, therefore, depending on the kind of scattering, either diffuse or specular, and this already you know from the knowledge of nanoscale transport. You know that these two are the possible kinds of boundary conditions you apply and solve from the Boltzmann transport equation. However, what happens, how do you incorporate this information into the continuum equation? Now, this is where it is becoming very tricky. If you solve the equation is through the approximation made by Kunt and Warburg. So, they have said that this is equivalent to giving a slip boundary condition at the wall, provided you know your slip boundary condition is related to the slip length. Okay. The slip length value is zeta times the velocity gradient at the wall. So, therefore, somehow the slip length should be related to this accommodation coefficient. So, the accommodation coefficient has the knowledge of the microscale scattering at the boundaries, and somehow in a ad hoc empirical manner that has to be accounted for through the formulation of slip length, and therefore, you assume the you know that the slip length can be related to the accommodation coefficient through an expression like this. That means, for example, in this case you can write this as 2 minus sigma by sigma times the mean free path of the gas molecules. So, this is one ad hoc way of expressing the relation between slip length and the accommodation coefficient. So, in the case of diffuse scattering, your sigma equal to 1, and therefore, your slip length will be equal to what? Lambda, mean free path. Okay. So, in the case of specular scattering, what will be the value? This will I mean, if you are approaching value of sigma going to 0, this value will go to infinity, right. So, the slip length is approaching infinity. Okay. So, these are two extreme limits, and between these two limits you know you can assume some values, something like sigma equal to 0.2 or 0.3 or 0.5, or if you know exactly the value for a particular fluid. For example, if you take the case of air, generally values of sigma are quite high, it is towards the diffuse side. So, it is between 0.87 and 1. Okay. So, if you take some other inert gases like argon, nitrogen, and also depends on the surface material. If you look at silicon material as a microchannel, and if you use nitrogen or argon or carbon dioxide, so the values of this sigma can vary between 0.75 and 0.85. Okay. So, they are always closer to the diffuse scattering. So, in that case you can assume also, if you have a rough interface, more likely this value of sigma will be closer to 1. Okay. And most of the practical surfaces have certain roughness. So, therefore, always the value of sigma is biased towards the diffuse scattering. Okay.
Maxwell velocity distribution is some function of some exponential type, or is there any distribution is available?
No, but when I mean that is correct, but the value of sigma theoretically cannot be calculated. Although we measure we define sigma in this way, you cannot use theory to calculate sigma. It is only coming from experimental conditions, where, as I said yesterday, how do you determine experimentally? You just extrapolate it, make a virtual origin and determine what is your slip length, and then now you have related your slip length with sigma, and therefore, you can reverse calculate, back calculate from experiment what will be the value of sigma. Okay. So, that is the standard procedure. So, therefore, this is one component of the velocity slip, and in many experiments they have observed that only theoretically, if you add this, the theoretical value of the velocity slip is not matching the experimental value. So, there is also something extra component which is causing an additional slip at the wall, which could not be explained by this particular term alone. So, later on then they understood that this was due to a phenomena called thermal creep. Okay. So, in which you also produce additional slip due to a temperature gradient. Okay. So, in addition to having a uniform temperature, in case where you have a temperature gradient, the gas molecules tend to move from the lower temperature side to a higher temperature side, that is in the direction of the applied temperature gradient. So, in addition to the normal Maxwell slip, okay, you also have an additional slip due to the thermal creep. So, the second term here represents the thermal creep slip. So, that is related to your temperature gradient, which is tangential, which is along the wall applied in the tangential direction, okay, whereas the velocity gradient is in the normal direction to the wall. So, therefore, these two components put together would adequately explain the slip velocities that are measured experimentally. Okay. So, in general, this kind of a slip boundary condition has become popularly referred to as Maxwell slip boundary. Some people also refer this term to this formulation, the formulation that we are referring here to Navier slip boundary. Okay. So, in the Navier slip boundary, you just give some value of slip length arbitrarily, it could be some 0.5 or 0.7 or 0.2, whatever it is, but if you want to relate it in terms of accommodation coefficients, then it becomes Maxwell slip boundary condition. Okay. So, and apart from that, you can also write boundary conditions for temperature, right. We have seen that you can have slip of both momentum as well as energy or temperature. So, therefore, this we have already seen in nanoscale transport. There is a temperature discontinuity at the boundary, and high Knudsen numbers, you will find this discontinuity will increase. therefore, to account for this, similar analogy has been drawn, in only that in place of the momentum accommodation coefficient sigma, we replace this with what we call as the thermal accommodation coefficient sigma subscript T. Okay. So, same analogy, except that we assume that these gas molecules with some energy is approaching the boundary, and fraction of that is absorbed and re-emitted based on the Maxwell-Boltzmann statistics, the other is reflected perfectly. So, but in this case, to distinguish this fraction from the momentum accommodation coefficient, we use notation sigma subscript T. Okay. And we once again rewrite same way to the velocity slip, we introduce a parameter called the temperature slip, which is the temperature of the fluid at the boundary minus the wall temperature. Okay. So, that is equal to a different slip length now. So, this slip length is called temperature slip length. Okay. The other is a momentum slip length or velocity slip length, this is a temperature slip length, and this has to be multiplied to the temperature gradient, right. So, if this temperature slip length is 0, then there is no slip. Okay, that is your conventional no slip boundary condition. And similar to the Maxwell velocity slip boundary condition, you can express the temperature slip in terms of the energy or temperature accommodation coefficients. So, that is we write now the temperature slip to be 2 minus sigma T by sigma T times parameters which are functions of the thermophysical properties, thermal conductivity, heat capacity, and so on. Okay. So, so this is actually popularly referred to as the Smoluchowski boundary condition, because Smoluchowski experimentally confirmed that this kind of equation can be used to match the theoretical value of temperature slip with the experiment very well, okay, using this parameter and knowing assuming values of sigma T. Okay. So, therefore, this boundary condition is referred to as Smoluchowski slip boundary. So, the velocity one is referred to as Maxwell slip, and the temperature slip is referred to as Smoluchowski, right. So, therefore, we can non-dimensionalize whether it is the velocity slip or temperature slip. As you can see that you have a mean free path here. So, if you non-dimensionalize your coordinate with respect to the characteristic dimension, characteristic length scale, for example, you introduce a new normal vector n star, which is equal to n by L, this is your normal coordinate, and similarly tangential coordinate as S by L. So, you can write this in terms of Knudsen number, and again the thermal creep slip due to thermal creep also can be written in terms of Knudsen number square, Reynolds number by Mach number square. Okay. So, therefore, sometimes these boundary conditions are also expressed in terms of only purely non-dimensional numbers. So, these are non-dimensional values of slip. Okay. Similarly, you can do the same thing for the temperature slip. You can write this purely in non-dimensional fashion. You get a ratio of Knudsen number by Prandtl number. Okay. So, therefore, once you now understand how this micro scale non-equilibrium at the wall can be incorporated into the continuum equation using these slip approximations for velocity and temperature, now it becomes quite easy to solve these governing equations for some standard cases like flow between two parallel plates, flow in a duct. So, these are some simple cases for which analytical solutions can be obtained. Only that now in the case of slip regime, you replace your no slip boundary condition with the appropriate Maxwell and Smoluchowski slip conditions. Okay. So, let us take the case of So, yeah, just to give some additional data, for sigma t, again for combination of air, aluminum, air, steel, you have different values also which are close to 1, whereas if you take clean surfaces without any deposition or which is quite smooth without much roughness, the if you use helium gas for example, this can be very small, okay, close to 0. So, this 0.02 is the value of the thermal accommodation coefficient. Okay. Therefore, similar to how we define the momentum accommodation coefficient, we can define this based on the difference between the incoming energy of the gas molecules and what is coming out divided by incoming minus what is emitted based on the Maxwell-Boltzmann distribution, right. So, I hope this is clear. So, this is the foundation of the slip flow regime. Okay. So, basically now that we have defined the boundary conditions, so we also know the conservation equations which are the compressible, Newtonian and isotropic case, and also the Knudsen number should be less than 0.1. This is where the continuum equations can be applied. So, this is called the slip flow regime. In this case, yeah, so you solve the compressible form of the Navier-Stokes equation along with this appropriate slip boundary conditions, and this can quite accurately predict most of the experimental results in this particular slip flow regime. Okay. And we will take the case where we can develop an analytical solution, that is, let us take a microchannel. Microchannel here means it is simply 2-dimensional case of flow between two parallel plates. Okay. So, just like you do your fluid mechanics of flow between two parallel plates, the same analysis is done here. So, we have to take the separation between the plates as distance 2h. Okay. So, therefore, the coordinate the origin starts from the center. So, it extends to plus h on to the top plate and minus h to the bottom plate, and you also assume the following things. So, one is number 1, you are looking at only steady state, a steady flow system. So, therefore, all the derivative with respect to time can be assumed to be 0. So, all of the d rho by dt, du by dt, dt by dt, all of this are gone, and the other important condition to simplify this is fully developed. So, you assume the profiles to be fully developed, meaning you do not have any gradients of velocity in the x direction. In this case you have z coordinate. So, in the z direction, and also this is a 2D system. So, you do not have any gradient in the third direction. So, based on this you will be able to see that so you can reduce the and also you can assume that there are no volumetric forces, and to first start the problem, the hydrodynamic problem, there is no heat transfer. So, it is all isothermal. So, with this you can reduce the compressible Navier-Stokes equation to the following form. So, you only have the viscous forces, the shear stresses, and the other is your pressure gradient. Okay. So, the viscous force is balanced by the pressure gradient. Okay. So, the viscous force in this case will be the diffusion only in the y direction, that is your d square u by dy square. Okay. And the pressure gradient will be in the z direction. So, your dp by dz, that means if you draw a control volume, you will have a viscous force on the top and the bottom plates, and this is to be balanced by the pressure gradient, and this viscous force is nothing but due to the diffusion of velocity in the vertical direction. Okay. So, therefore, the entire compressible equations reduce to a very simple form which is similar to your incompressible equation for channel flow. Okay. So, therefore, there will not be any big difference between compressible and incompressible now that you have assumed a steady state and fully developed flows. And then we go on, we apply the boundary conditions to solve this. Now, the condition at y equal to 0 will be symmetry, right. So, we have taken the origin to be at the center of the channel, and therefore, at y equal to 0 you can say that the velocity profiles will be symmetric between the top half and the bottom half, and you can simply apply the symmetry condition, which is du by dy equal to 0. Okay. And on the other side, so y equal to plus h, in the conventional channel case you will give the no slip condition, which is u equal to 0, but now you give the Maxwell slip boundary condition. Okay. So, therefore, you have both of both boundary conditions. One is the slip boundary condition on one side, the other is the symmetry boundary condition, and you substitute these two. You can now, this is an ODE which you can directly integrate it a couple of times to get the velocity profile. So, this is a very simple case, and if you do that, you get your solution, general solution for the velocity profile like this. It is a quadratic equation. So, in order to get the constants a1 and a2, you apply the two boundary conditions at y equal to 0 and y equal to h. So, can you try to do this now? So, you apply these two conditions, find out the constants and calculate how the velocity profile looks. This should be, let me check if I think in this case the derivative is negative, no. So, your velocity profile is maximum at the center, and at y equal to h it will be negative. So, in order to get a positive value, you put, I think, a negative sign here. Your du by dy will be negative, right. So, in order to make sure your velocity is positive, therefore, you put a minus sign there, right. Otherwise, you get a negative value of velocity, which is not physical. So, in the case of no slip, you will get a2 equal to 0, but here you have a value of at y equal to 0, right. Yeah. Yeah, a1 is 0, right. So, you should be getting something of this form. This is non dimensionalized here, where I write u star as u z by u z naught, where u z naught is value of u z at y equal to 0 and Knudsen number equal to 0. Okay. So, that is your center line profile corresponding to Knudsen number of 0. Okay. If you put Knudsen number of 0, so you get 1 minus y star square, okay, and at y equal to 0, that is the maximum value, right, maximum value at the center line corresponding to Knudsen number of 0 y equal to 0. So, therefore, now the difference between the slip and the no slip velocity profile is, if you simply substitute Knudsen number of 0, you get your profile for the no slip boundary condition case 1 minus y star by 0. So, y star is nothing but y by h. So, therefore, you get your conventional parabolic profile with the maximum at the center line. Now, apart from that, you have the additional factor which is dependent on the accommodation coefficient coming from the boundary condition. Okay. From this you can evaluate what is your mean velocity at a given cross section. You can integrate the velocity profile from minus 1 to 1, that is, or minus h to h, and you can calculate the value of magnitude of the mean velocity profile, mean velocity, and that comes out to be 2 by 3 plus 4 times 2 minus sigma by sigma Knudsen number. Now, the way we have defined Knudsen number prime, I think that is small, that is basically 2 times root 2 times your Knudsen number. Okay. So, you can just leave it as Knudsen number, there is no problem, you do not have to write in terms of Knudsen number prime. So, essentially if your sigma is 0, okay, for example, for the specular case you can say that the value goes to very large values of u star, and similarly if sigma equal to 1, so what will be the value? So, it will be simply 4 times your Knudsen number prime or 8 times Knudsen number. Okay. So, if your Knudsen number is going to 0, then this becomes equal to 2 by 3. Okay. So, therefore, depending on the value of Knudsen number, now the higher the value of Knudsen number, the larger will be your value of the mean velocity, right. So, what you are seeing is that for a given, therefore, for a fixed value of pressure drop, as your Knudsen number keeps increasing, the average velocity also keeps increasing because of the higher slip. So, that means you are getting more mass flow rate for the same value of pressure drop.
So, somewhere a negative sign is missing, we are actually getting y star square minus 1 and sigma minus 2.
Instead of 1 minus y star square, you are getting y star square minus 1, is it?
And also
If you had applied this minus sign, is it?
yeah, we applied that
Minus sign. If you do not apply the minus sign,
we will get this one.
Okay, probably there is an error, because this is your correct profile, because at Knudsen number equal to 0, it gives back your macro channel velocity profile. Okay, so probably then this minus sign is not needed here. Okay, you please check that. If you get opposite sign, then you remove the negative sign there.
If we not use that negative sign, then it will come that y 1 plus y star square.
Then so then you are getting correctly, is it?
Y plus y star square.
1 plus y star square.
Yeah. 1
But if you use the negative, are you getting 1 minus y star?
y star square minus 1.
Minus 1.
Yeah.
Hmm. There should be a the momentum equation should have a minus sign. The momentum equation itself should have a minus sign there, because the viscous force and pressure gradient are in the same direction right now. See, in the these are both in the right hand side, right? So this is at minus dp by, yeah, I think then it's, this is okay. I think there is so if you have a negative sign in the momentum equation, will that be fine? It will make it 1 minus y star square. Or the other way of evaluating it, apply this at y equal to minus h, okay, y equal to 0 and y equal to minus h with a positive sign, and see if you are getting the same profile. If you get that, then you use the bottom half rather than the top half. Okay, so in the bottom half, your slip at the wall should be 2 minus sigma by sigma lambda into du z by dy. But this should also work out, I do not know, but the final equation is correct. Okay, you just please check where you are going sign.
We'll try again.
Yeah. So this is your final equation in terms of Knudsen number. Now you, therefore, depending on the value of Knudsen number, you get additional average velocity or additional flow rate because of the slip. Okay, so therefore you can go ahead and you can find out the other integral quantities like the skin friction coefficient. You can calculate your wall shear stress based on the gradient of velocity at the wall, and therefore you can calculate your skin friction coefficient and so on, and you can also calculate the pressure or the Poiseuille number. So that Poiseuille number is nothing but basically friction factor times your Reynolds number. Okay. So therefore the skin friction, the friction factor that you have defined here, this is called the fanning friction factor. This is in terms of wall shear stress by half rho u square. So this is similar to your skin friction coefficient for external flows. So the other friction factor which you can define is in terms of pressure drop, that is called the Darcy friction factor. So therefore if you write down the relationship for Darcy friction factor in terms of Reynolds number for a circular duct. So for the case of macro ducts, you get F is equal to 64 by Re, or in terms of the Cf that you have written here, it will be 16 by Re. Okay. So the product of the friction factor times Reynolds number is called the Poiseuille number. In the case of macrochannel circular ducts, your Poiseuille number is equal to 64. Now in the case of microchannel ducts with slip boundary condition, this will become a function of the Knudsen number. Okay. So therefore the product of friction factor times Reynolds number will not be a constant anymore, it will be a function of Knudsen number. For the case of Knudsen number going to 0, this will go to the value of 24, which is the case for channel flow. Okay. For duct flow you have 64, and for channel flow you have 24, right. So you can write therefore the Poiseuille number as a function of Knudsen number through this particular expression. So what it tells you that if you are increasing your Knudsen number, what happens to the Poiseuille number? it will reduce. Okay, that means your for a given flow rate your pressure drop is actually lower, or for a given pressure drop you get higher flow rate. So, this is the effect of slip at the walls. Okay. So, this is good as far as the pressure drop is concerned. So, if you are pumping certain flow rate, right. So, the pressure drop required to drive this in the micro channel will be lower than in the macro channel case, right. Or if you apply the same pumping pressure gradient to pump the flow, you get a higher flow rate, right. So, this is a beneficial effect of the gas flows in the slip regime of the micro channel. So, therefore, we can also calculate what is called as a non-dimensional mass flow rate, which gives you the actual mass flow rate calculated from the slip boundary condition divided by the mass flow rate calculated from the no slip boundary condition. Okay. So, obviously, the numerator is larger than the denominator. Okay. So, this comes out to be again a function of the accommodation coefficient, the pressure gradient, pressure ratio. Okay. So, the denominator here has nothing but the pressure ratio between, that is the ratio of the inlet and outlet pressures and the Knudsen number. Okay. So, if your Knudsen number is equal to 0, this non-dimensional mass flow rate will be equal to 1, and for larger Knudsen number this will be greater than 1. So, that means as your Knudsen number keeps increasing, this non-dimensional mass flow rate will also subsequently increase. So, therefore, when you plot the non-dimensional mass flow rate as a function of Knudsen number, okay, so the reciprocal of this should keep decreasing with respect to increasing Knudsen number. So, as your Knudsen number keeps going up, higher will be the flow rate, or the inverse of this should be lower, right. So, depending on the value of the accommodation coefficients, you can get different values, and also if you are going to slightly larger Knudsen numbers, for example, here the Knudsen numbers have crossed for example 0.2, 0.3, 0.4, and as we said Knudsen number of less than 0.1 is where we use our slip model. Now, what happens when you cross 0.1? Suddenly the slip model fails and continuum fails? Not exactly. To be more accurate, we have to go to what is called the Burnett equation, but sometimes people still use the continuum equation, but they modify the slip from first order to a second order slip. So, they incorporate a higher order slip boundary condition, which includes terms d square u by dy square. Okay. So, with that you see that if you use just a first order slip beyond Knudsen number of 0.1, these symbols are actually the experimental values, and whatever is computed is basically these lines. So, if you use the first order slip boundary condition, you get a good agreement till Knudsen number of 0.1. For higher Knudsen numbers you do not get a good agreement, whereas if you use a second order slip, even for Knudsen numbers of up to say 0.2, 0.3, you are able to get a good agreement. So, beyond that even the second order slip will not be able to match with the experiment well. Okay. So, therefore, coming to the heat transfer problem, okay, we solved the fluid mechanics problem for velocity profile. Now, we can also solve the energy equation for fully developed both hydrodynamically and thermally. So, the energy equation will be similar to the macro scale parallel plate energy equation. Now, we will, the only difference is we will be applying the slip boundary condition at the other wall. So, at y equal to 0 you still have the symmetry boundary condition, and at y equal to h you have the slip boundary condition. So, just to summarize that, if you, I am just skipping all the details, these are available in your in a textbook, any textbook related to microchannel flows. The book that I am following is by Satish Kandlikar and Srinivas Garimella. Okay. So, this is flows in micro and mini channels, heat transfer in micro and mini channels. So, by Satish Kandlikar and Srinivas Garimella. So, I think this is a pretty straightforward analysis similar to the macro channel. The only difference comes in terms of the boundary conditions, that you apply slip boundary condition at the wall, and similar to your velocity profile, okay, you get your temperature profile. Now, this zeta star here is nothing but a function of your accommodation coefficient and Knudsen number and Prandtl number. This is coming from the slip boundary condition. So, all these are written in non-dimensional form, and therefore, this is your expression for your temperature profile, and from this if you calculate the Nusselt number at the wall, the Nusselt number also turns out to be a function of the accommodation coefficients and the Knudsen number at the wall. So, if your Knudsen number is equal to 0, this value of zeta star will be also 0 at the wall. So, in that case, for the limiting case where your Knudsen number equal to 0, this Nusselt number will reach the value of 140 by 17. Okay. So, which is the value of Nusselt number for macro channels, for heat transfer in macro channels. Okay. So, for the larger Knudsen number case, you use this particular expression to calculate the actual heat transfer coefficient. So, what happens now due to the temperature jump, okay, what happens to the temperature gradient at the wall? So, originally your temperature profile, if you see, look at the profiles that I have plotted here. So, your original temperature profile was 1 without any slip. Now, your temperature profile is shifting towards 2 with slip. So, what happens to the temperature gradient at the wall from 1 to 2? So, your mainstream value, assume that this is constant. What happens from 1 to 2? Decreases. Okay. So, if your temperature gradient decreases, what happens to a Nusselt number? Heat transfer coefficient also decreases. So, therefore, although the pressure drop decreases, consequently the heat transfer rate, convective heat transfer coefficient or Nusselt number also drops. Okay. So, from the hydrodynamic point of view, it is very convenient to operate with slip flows, but from heat transfer point of view, it is not so beneficial, right. So, therefore, if you are looking at larger Knudsen numbers, the value of the Knudsen number, the Nusselt number will be reducing as given by this particular expression. Okay. So, whereas for the macro scale case, it comes back to the classical value of 140 by 70. Okay. So, therefore, I will just summarize a scenario where you have now circular micro tubes. So, in the micro tubes, you have to rewrite your conduction term slightly different. Your diffusion term will be 1 by r d by dr of r du by dr. Okay, it is not, whereas in the channel case it is just d square u by dy square. So, similarly for the heat transfer also. So, in this case the velocity profile, the mean velocity will be described in this particular fashion, that is the mean velocity profile will be half of your center line value, correct, in the macro channel case. Now, that is going to be slightly different with higher Knudsen numbers. Similarly, the Nusselt number is also described by this equation. So, you see that for the case of Knudsen number going to 0, the Nusselt number will be now 48 by 11. Okay. So, that is 4.36. That is the case of constant heat flux laminar fully developed hydrodynamically and thermally in a circular duct. That is your macro scale case. Now, in the micro duct micro tube case, these values are smaller than 48 by 11. Okay. So, this expression can be used similar to the channel case. Channel case you have a different expression, and circular microtubes you have this expression. So, this is the summary, for if you want to calculate heat transfer for gas flows in microchannels. So, for a 2D microchannel you use the expression on the top, and for the 3D microchannel for a circular tube you use the expression on the bottom. Okay. And if you plot these, you can basically see that the parallel plate case has a higher value of Nusselt number compared to the circular tube, and again for different values of the momentum and the thermal accommodation coefficients, you can produce different values of Nusselt numbers. So, these are functions of accommodation coefficients as well as the Knudsen number. Okay. So, as your Knudsen number keeps increasing, your Nusselt number reduces. Okay, just a last topic I want to complete this portion. So, as we said, all these analysis is good if you are looking at Knudsen numbers of up to 0.1. If you are going to higher Knudsen number with the use of second order slip, to some extent you can still solve the continuum equation, but we are going away and away from the assumption of continuum, and therefore we have to resort to finally going back to the Boltzmann transport equation for larger Knudsen numbers, and for Knudsen numbers greater than 1, definitely continuum equations cannot be used. But what can be done is solving the Boltzmann equation is also computationally very expensive, especially if you have 3 dimensional flows. So, one alternative is people from the Boltzmann equation use what is called as the Chapman-Enskog expansion. Okay. So, this is a very classic way of deriving all the continuum equations starting from the Boltzmann equation. So, this Chapman-Enskog expansion is done from the Chapman-Enskog expansion. For example, for the viscous stress tensor and the heat flux vector, you get several terms starting from the lowest order approximation to, if you include all the terms together, so that will be your equivalent to solving your BT. Okay. So, if you remove all the higher order terms and use only the lowest order term, that is your lowest order approximation. So, therefore, if you expand your viscous stress tensor and your heat flux vector based on the Chapman-Enskog, you end up in getting a series solution with starting from the lowest order to the highest order terms, and if you are taking only the lowest order term, okay, so that will give you the Euler equation. For example, if you are retaining only the 0th order term here, so the 0th order term will be nothing but there is no viscosity, viscous flux is equal to 0 and heat flux is equal to 0, that means there is no diffusion. So, this is nothing but the Euler equation. Whereas, if you incorporate both the 0th order and the first order terms together, you get your Navier-Stokes equation. So, any other higher order terms that you incorporate will be giving you better solutions for higher Knudsen number. Okay. So, therefore, what people did, they just also incorporated the second order terms for larger Knudsen numbers. So, with that including the 0th order, first order and second order terms together, you get what is called as the Burnett equation. So, I am not writing down the equation, these are very large equations because of so many terms, okay, but nevertheless when you look at Knudsen numbers greater than 0.3, 0.4, people have to inevitably solve these Burnett equations, and these Burnett equations can give a better solution compared to the continuum equations. Okay. So, with that we will kind of stop this portion on gas flows in microchannels. So, most important aspects I have covered. The next topic that we will be looking at is liquid flows in microchannels. Okay. So, before we go on, I think I will anyway stop here, but you should understand that liquids in the sense of Knudsen number, so have much smaller Knudsen numbers for the same diameter ducts that you are talking about compared to gases. So, therefore, hardly you go into the slip regime itself. So, you are most of the times talking about Knudsen number values less than 0.01, okay, even for duct diameters of the order of few microns. So, usually in liquid flows you do not have any problem using the continuum equations also with the no slip boundary conditions. Okay.